Cover the mean and standard deviation of a binomial variable. In a binomial distribution, we're repeatedly performing the same experiment over and over again, and we're counting successes. The mean is represented NP, and it represents the average number of successes we expect after many trials. An example would be if the probability of success is 20% and we perform 100 trials, we would expect about 20 successes on average. The standard deviation measures how much the results typically vary around the average, and we've discussed that previously as well. Because the variability depends on both successes and failures occurring together, we have to use a different formula. If our probability becomes very close to 0 or 1, the outcomes become more predictable and the spread shrinks. Spread is another word for variability. But probabilities that are near 50% create much more variability because the outcomes are less predictable. We're going to learn how to calculate the mean and variability in terms of both variance and standard deviation for a binomial distribution where each trial results in either a success or a failure. And we've talked about binomial distributions and binomial probability in our previous lessons. So before we even get to our example, let's take a look at some notation and some of these formulas that we need to know for mean and standard deviation of a binomial random variable. So for a binomial random variable, we're repeatedly performing the same trial. There's only two outcomes for a binomial, success or failure. And the same probability of success happens each time. Also, trials are independent. These formulas come from analyzing what happens when we add many independent Bernoulli trials together. And the notation is X is binomially distributed with parameters NP. And X is really the sum of X2, should write X2 there. It is the sum of each individual trial all the way to Xn. If a success occurs, we have a 1, and a failure, there's a 0. And these are called Bernoulli random variables. For one Bernoulli trial, success is the probability that X equals 1, since we define 1 as success, and we write that as P. For a failure, that's the probability that X equals 0. And this is the complement of the success, 1 minus P. This only works with a binary yes/no outcome or a success/failure situation. Now, we've got to figure out really how we're even deriving the mean in terms of this equation. So to figure out what our average is, it's the expected value over the long run average. So for one trial, we can say that the expected value is equal to success, which is 1, times P, because we said the probability of a success is equal to P. Let me just go up here actually so we can see that. Plus failure times the probability of failure. That's going to be our expected value. And when we multiply this 0 times 1 minus p, we just get 0. And so our expected value is just going to be p. So each trial contributes an average of p, is what we would say. If we did n trials, where n is the number of trials, because we were talking about earlier when we add x all the way x1, x2, x3 all the way to xn, if we had n trials, then we would write the expected value as the number of trials times p, or np. And this gives us the binomial mean formula. So for binomial, the mean is equal to np. And we're going to be using that formula. I just wanted to show you a quick proof of where this formula is coming from. Next, we're going to look at variance, and we've calculated variance in previous lessons, but now we're going to look at, again, a variance with binomials. So for one Bernoulli trial, for just one trial, the variance is equal to, or the variance of x is equal to p times 1 minus p. That's for one Bernoulli trial. Um, but variability depends on the chance of success and the chance of failure. Um, so we've got to rewrite our variance formula. Remember, if p equals 1, that means that success always happens and there's no variability. If p is 0, then there's also no variability because we have a failure. So the maximum variability would occur at p is 0.5. And that's just kind of a side note. So if we want to know what is the most variability that we have, that would be at p equals 0.5. So the variance can be viewed as the binomial mean multiplied by the probability of the failure. So we've already defined that our mean is NP. And so to write the variance over many trials, we would write it as the variance of X is equal to NP times 1 minus P, times quantity 1 minus P. And NP is also mu, the mean. So we could also write this as the variance of X is equal to mu times quantity 1 minus P. Okay, so that's our variance formula. And then if we needed to find the standard deviation, all we'd have to do is find the square root of that. Because the variance of X, we could write this as the variance of X, maybe like that. That is equal to mu times 1 minus P. And so the standard deviation would just be square root of each. And hopefully this is review for you. So now we would have the square root of mu times quantity 1 minus np, or we can write it np times 1 minus p. Same thing since mu equals np. Okay. All right. So now we've got these proofs and these formulas that we can work with in terms of our mean and our variance. So let's go to our example problem finally and take a look at uh, what it wants us to find here. So it says a company produces processing chips for cell phones. At one of its large factories, 2% of those chips are produced are defective in some way. A quality check involves randomly selecting and testing 500 chips. What are the mean and standard deviation of the number of defective processing chips in these samples? Okay, so let's define N and P. We'll start with that for our first step here. We're going to define N and P. So N equals 500. So we have 500 chips that we're testing, and the probability that it's defective is 2%, 0.02 is what P is. So now we're going to calculate the mean. And the mean is equal to NP. NP. So just 500 times 0.02, excuse me. And that's going to give us our mean. And so our mean is going to be 10. So the average number of chips, or the mean chips that are defective, would be 10. And again, this formula only works because it's we're talking about binomial random variables. So it's either defective or it's not defective in this specific case. Okay, now we're going to calculate the variance. And our formula for variance is the variance of x is equal to NP times quantity 1 minus P. And we know both of our values for N and P. We know that NP already is equal to mu, which is 10, so I'll just write that as 10. 1 minus P is 0.02. Okay, and then we're just going to multiply this out. And we get 10 times 0.98, and this is going to be 9.8. Okay, so that's the variance. Let's take a look at our question now. It says it wants us to find the standard deviation. So the last thing we're going to do is we're going to take the square root of both sides. So just say find standard deviation for step 4. So we know that the variance is equal to 9.8, and we're just going to take the square root of both sides to find the standard deviation. And I got approximately 3.13. And it looks like they're asking us to round to the nearest tenth in this problem. So we'll write standard deviation is 3.1. Okay, so it has a mean of 10 with one standard deviation of 3.1, or we can say plus or minus 3.1. Okay. All right, let's take a look at one more. I think it's essentially the same type of problem, but we'll just do one more example here. 60% of a certain species of tomato lives after transplanting from pot to garden. Eli transplants 16 of these tomato plants in a garden each month. Assume that the plants live independently of each other. Let X equal the number of tomato plants that live in each month. Find the mean and standard deviation of X. Okay, so we're going to again define N and P. And N equals 16. P, the probability, is 0.60. Now we're going to calculate the mean. And that's going to be, the mean is equal to NP. And that's 16 times 0.60. And that's 9.6 for our mean. So that's part 1. 9.6 tomatoes is our average. Okay, now we got to find our standard deviation using our new variance formula for binomial random variables. So the variance of X is equal to NP times 1 minus P. We already calculated NP, which was the mean, and that is 9.6 times 1 minus P is 0.60. So now we've got the variance of X is equal to 9.6 times 0.40. And it looks like we're going to get 3.84 for our variance. And then our last step, we're going to find the standard deviation. And again, we're just going to take the square root of both sides to do that. So the variance of X is equal to 3.84. Take the square root of both sides and we get the standard deviation of X is equal to approximately 1.9 0.59. And this problem also wants us to round to the nearest tenth. So this one's going to round up to 2.0 for our standard deviation. Okay. So I think once we have those formulas, these problems aren't that bad. But hopefully the proofs of the formulas were helpful as sort of an introduction for this. Okay, so that is everything on this section.